Hello, welcome to the first video from chapter 33. So the last big unit that we're going to cover is on light, optics. Now, so your book spends the first section of this chapter talking about models of light. Sometimes it makes more sense to talk about light as a wave, and sometimes it makes more sense to talk about light as a ray or a particle. Now, different models of light help explain different phenomena of light. And it's impossible to say one way or the other whether light is a wave or a particle. It's both. So just as a general overview, chapter 33 is exploring aspects of light where it makes more sense to think of light as a wave. So that's why the chapter is called Wave Optics. But later, so the next few chapters after this, chapters 34 and 35, we'll be talking about ray optics, or so-called geometric optics, where we talk about light as a particle. So we'll talk about things like lenses, Snell's law, things like that. But this chapter, to focus on light as a wave, one of the most striking properties of waves is interference. If you have interference, you definitely know you have some wave-like property. Right? Particles don't interfere in the same way that waves do. And so there's an experiment that really, the wave-like nature of light really hits you in the face. And that's called the Young's double slit experiment. And that's what we're exploring in this video. So to give you an overview, you have light coming in. So right here, this is laser light coming in. We'll talk a little bit more, but it has to be coherent light coming in. So so by two slits, we literally mean a screen where we just poke two holes in the screen. So these holes then act as sources for light. So the light will come out of this source or this source and project onto a screen. Now, if light were a particle, it would just kind of, you shine light to the right, so you would expect just two bright spots, one for each of for the two slits. But what we actually see on the screen is a bunch of different bright spots, a lot more than two. So dozens and dozens, potentially. So we want to be able to explain this, and we can be a little bit quantitative about this, and we can relate the distance. So for example, what I drew here are the positions of the bright spots, and by delta y1, that's why I'm going to say the change in distance along a screen from one bright spot to the next. So we can actually explain that quantitatively. So we'll need to bring up things like the slit distance. So we're going to introduce d is the distance from the center of one slit to the center of the other slit. We're going to need to describe the positions on the screen. So we can talk about the y coordinate relative to y equals 0, or we could talk about angles. So we'll also talk about angles relative to the center here. Yeah, so we'll introduce the quantities in a little bit, and then once we build up this quantitatively, we can answer this question about how this interference pattern will depend on wavelength of the light. Another overview. So this is an overview just of this chapter now, of chapter 33, and where we're going with the next few videos. So the double slit experiment is the easiest to describe this wave phenomenon. So we're going to start, so 33.1 is just an intro to models of light. 33.2, we go into the interference of light. And the double slit experiment, Young is, by the way, is a person's name, Young's double slit experiment. So two slits is the easiest quantitatively to describe. And then we're going to talk about multiple slits in section 3, 33.3. And this is, it's called a diffraction grating. But that's sort of a terribly, it's sort of a terrible word for this, because the chapter is split into interference and diffraction effects, and we normally think of diffraction for something else. So diffraction grating is actually an interference phenomenon, not a diffraction phenomenon. So we're going to generalize what we do in this video in later videos to multiple slits, and then we'll talk about what happens with just a single slit. And that's what's called diffraction. And then the next section, 33.5, we're going to incorporate both aspects. So aspects from sections 33.2 and 33.4 to talk about both effects. So in this video right here, we're going to ignore the slit width. So I said we're going to poke a hole right here. So we're going to imagine that the hole is infinitely small. Okay, so if it's not infinitely small, then we have to incorporate diffraction effects, these single slit effects, and that's what we're going to do in a later video. So we poke hole, we have to allow some light to get through, but we're going to imagine that the slit, the hole is very, very small compared to this distance between the two slits. That's what we're assuming in this first video. That'll be the easiest to describe mathematically. Okay, I want to also give you a reminder, because the reason that this interference pattern exists is that light is a wave, and waves will interfere with one another. So I want to remind you about constructive versus destructive interference. So remember, we had the path length difference. So this is just some number, and the number we want to relate to the number of wavelengths. So this right here would be a number of meters. And you can say, well, I have 1.5 wavelengths or 3.2 wavelengths. You can have any value of m right here. So you're just writing the path length difference in terms of wavelengths. And if m is an integer, so if m is 0, plus or minus 1, plus or minus 2, etc., then you have constructive interference. And if m is a half integer, so this is just getting at the where they're going with the next few sections, but we're going to focus on light as a wave. So your book is doing this brief review of interference. I'm not following their convention here. So here they have two different formulas requiring m is always an integer. No, I'm not doing that. I'm just saying that this is the one formula, and m could be anything. And if it happens to be an integer, it's constructive interference. And if it's a half integer, plus or minus 1/2, plus or minus 3/2, etc., then it's destructive interference. So the reason we see bright spots right there is that so like this bright spot right here, the path length difference, so the distance from this bright spot to this slit is a little bit shorter than the distance from this bright spot to that slit. And how much shorter? Well, it's shorter by exactly 1 wavelength. And that's why we see constructive interference, because it's an integer number of wavelengths. This bright spot right here is going to be closer to this slit than it is to this one by 2 wavelengths. And that's why we see a bright spot there. For the dark spots, so right in between the bright spot right here and there's a dark spot right here, and that's exactly destructive interference. So this is the first one. This is where the path length difference is 1/2 of a wavelength. So if I drew a line to this one and I drew a line to this one, they're off by 1/2 a wavelength. That's why we see a dark spot there. So this requires, so remember, this is if the sources are in phase. So we're assuming, so the sources are coherent and in phase. So this phenomenon doesn't work if you just shine, if you take a light bulb, an old light bulb where you're heating up tungsten and you just shine it on this thing, you don't see this interference pattern. You do see it with laser light. So laser light has just one wavelength, and the light that's going through right here, through this slit, and the light that's going through this slit are in phase. When one is a maximum, the other is a maximum. So sometimes you see pictures where people are drawing the wave not in this ray model, but they're drawing the wave crests. So this is like where the maximum of the wave is reached. And notice how when one of these, so imagine this propagating to the right, when one of these wave crests crosses this one right here, this slit right here, it's also crossing through here. So they're in phase. So the light that's passing through each of these slits starts off in phase, and the only reason there's a path length difference is the path length difference, the difference in distance covered. Okay, so that's the reminder of interference that we talked about in the chapter 17 video on interference. So it's the same thing going on here. It's just a wave phenomenon. We just happen to be focusing on light here. Okay, at this point in the video, I want you to, so in the video description below, there's a link to a demo. So we can't do a demo really via the video, but I can link you to to other videos. So one is a demo of, I think it's MIT, and I just want you to see the setup of this. So I want you to see that they're shining laser light through two slits, and then they see a pattern. And then this demo also changes something. So they're changing the slit width and the distance from the slits to the screen, etc. So I just want you to quickly glance at that video and just see what we're talking about, so that it's not just random pictures here. And then I'll also link to some Khan Academy videos describing the setup. So I'll talk about it in a slightly different way, but those videos are actually pretty good. So I'd encourage you to watch those, especially if this video doesn't make sense. Okay, so Young's double slit. Experiment. So yeah, there's two different representations. So this one's just kind of a photograph. So someone's like taking a picture behind of the setup, and then this is the picture on the right here is normally how we draw pictures with this. So we have the double slits. So remember, we're assuming that they're infinitely small in width right here. So the distance here is d. So a lot of the picture that I'm going to draw is just setting up the variables that we're going to define. So the center to center distance between the two slits is d. So this is our double slit. And then we also have a screen back here. So this is really, it's just like a wall. It's nothing special. It's just, the light is passing through the air, and we only see it when it bounces off something. So it could be a wall, it could be a whiteboard, a blackboard, could be anything, right? Could be your couch, doesn't matter. So we're going to talk about positions on the screen, and we can talk about it a few different ways. So first of all, there's a middle spot on the screen. So one way we could talk about positions is to just define this is y equals 0, and this is the y direction. So y is a distance from the center of the screen, and the center is defined by you take the center of the slits and you go straight towards the screen. And we're not going to tilt the screen or anything. The double slit and the screen are going to be parallel to each other. So this position on the screen would be maybe 1 centimeter away from the center. So y equals 1 centimeter. Another way of talking about positions on the screen is to talk about angles. Okay, so this position on the screen is a certain angle relative to, let's see if that's pretty close to a straight line. That's a certain angle relative to the center line. So again, there's some special center line here. That's ugly theta. So I can talk about a position on the screen via theta. So one idea here is that the position on the screen we can labeled with either y or theta. So notice how for both of, so this position on the screen right here is y equals 0 or theta equals 0. And then customarily as we go up, it's positive y in meters or positive theta in radians or degrees relative to the center line. Now, if you read this chapter, you might notice they're defining theta. It looks like a little differently. It looks like they have a different theta for each of the two slits. So what we're always going to be operating under the assumption that this slit distance d is much less than the distance to the screen. So we're always operating under the assumption that the light rays coming out here are approximately parallel. Okay. So notice how like they have the same theta right here. So we could also just say that, that there's in the center right here, and then another line coming out parallel is the same angle theta. So there's, so right now it looks kind of confusing because they have a different theta, but you should think of theta more so like this, as theta is labeling positions on the screen. Okay. Okay. So we also have, I should start using a different color. We also have, I think that's green. I think this is brown, and this is green. I'm colorblind, so that's where it comes in. Now the distance from the double slits to the screen is L. Okay. So we're gonna eventually have an equation that's gonna have a whole bunch of different parameters, a whole bunch of different variables. So I just want you to be familiar with all of these. Okay. So the gist of the proof here, so your book goes over this, the Khan Academy goes over this, video goes over this. The gist of this is that, so we're going to take a position on the screen and so we have the center line, we have this right here, so we can draw two different lines to our point. We have the line from there and the line from here. So they're coming out approximately parallel. And the distance is actually, so really I should have these really, really close to each other because we're assuming that the light rays come out approximately parallel. So they don't look very parallel right here, but it's because we exaggerated the distance here. Exaggerated the distance d. So the path length difference, so if you look at all the proofs here of how they derive the path length difference, books will draw like this line that's perpendicular to the shorter path. So in other words, the distance from here to here is the same as the other path. So the path length difference is just this little piece right here. This piece right here is the path length difference. It's how much farther the path on the bottom has to go than the path on the top. And you can show that in terms of d and in terms of theta, which was the point on the screen relative to here, so this angle theta, you can show that the path length difference is d sine theta. Okay, and that's the key result of this whole section. Or at least it will be closely related to the key result. So the key result, we have to relate this to our statement about interference here. But that path length difference is d sine theta. So this makes sense that when theta equals 0, we get no path length difference because it's exactly the same distance, right? But as you increase theta, the path length difference increases. Okay, so all we need to do is set our path length difference, d sine theta. So I'm using delta x, your book's using delta r, but they're referring to the same thing. D sine theta is m lambda. Okay, and really this is what we care about. So if m is an integer, so I'm just repeating down our statement about interference. If m is an integer, equals 0, plus or minus 1, plus or minus 2, we get constructive interference. And in the context of this double slit experiment, we get bright spots. These are the spots of maximal intensity because the two light waves will add up constructively. So these are bright spots. If m is a half integer, plus or minus 1/2, plus or minus 3/2, etc., then we get dark spots, points of destructive interference. Now I like just having you remember one formula rather than, so your book does a separate like bright spots, and I guess they don't do the dark spots, but yeah, they do. I hate this. So they're having you try and remember like a different formula for bright spots versus dark spots. Don't. It's just this one formula. The path length difference is always d sine theta. If that happens to equal a half integer number of wavelengths, then that's where the dark spots are. So remember in the picture before, and if you looked at the demo in the linked article, you would see a bright spot here, 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 bright spot here. You can label these bright spots with their value of m. So m equals 0 would be this bright spot. M equals 1 would be this bright spot. M equals 2 would be this bright spot. M equals minus 1, M equals minus 2, and this goes on forever. Now these dark spots are exactly halfway in between. So this point right here, exactly halfway between these two. So long as these are equally spaced, you know, in the small angle approximation. This spot right here will be m equals plus 1/2. And this dark spot right here will be m equals 3/2. It's the next one. It's between 1 and 2. And this one right here is m equals 5/2. So those are points of destructive interference in between the bright spots, which are points of constructive interference. Okay, so for those special values of m, you can solve for where those positions are on the screen. So notice how if we know the light's wavelength, lambda, and we want to know a particular bright spot or dark spot, we can plug in that value of m. And assuming we know the slit separation, we know exactly what those angles are going to be. Okay. One other thing, so in the small angle approximation, so we haven't used this capital L, remember? The capital L, the distance from the slits to the screen. In the small angle approximation, we can relate theta and y. Remember, the y labels the values along the screen. We can relate them pretty easily. So in the small angle approximation, let me draw this, let me draw the screen, let me draw the center line, let me draw a point right here. In the small angle approximation, you can say, well, this is y, this is theta, and a lot of times you'll see that the angle that we have is going to be really, really small. So if that's theta, that's L, and that's y, we can relate these with sine theta is approximately equal to, and this is where the small angle approximation comes in. So if theta is in radians, we're going to say theta is very, very small. Theta is much, much less than 1. So sine theta is approximately equal to theta, or tangent theta. So all of these are the same if theta is small. So this is opposite over adjacent. Right? This is a right angle right here. So this is y over L. So looking at this first piece and the last piece, we can replace sine theta with y over L. So if theta is small, then our path length difference becomes not just d sine theta, but d times y over L. And then that is equal to m lambda. So this is just the same formula over again, but plugging in the small angle approximation. And the reason this is useful is sometimes you want to know positions on the screen in terms of meters rather than angles. Sometimes it's easier to measure, like you take a ruler up to the bright spots and you can measure the distance between the bright spots. Actually, this reminds me of one other thing. So notice I labeled here delta y1. And I meant by that the distance from one bright spot to a consecutive bright spot. Okay, so what do I mean by that? I mean, so I can label, so d times, let's say I'm looking at the mth bright spot, d times ym. I don't want this to look like a differential, so I'm going to put the d on this side. So just the slit separation d times a positional on the screen corresponding to the mth maximum. So I'm going to assume this is an integer right here. Right, I want to talk about a position of a bright spot over L equals m lambda. And then I can also talk about the next one. So the position of the next bright spot, so m plus 1. So I'm just going up to the next bright spot. This equals m plus 1 times L. So if I call this equation 2 and equation 1, I can do equation 2 minus equation 1. And what that gives me is, so delta y is the change in distance between any two adjacent bright spots. So this one means that the difference is just the difference between two, you're jumping from one bright spot over to the next one. You're just jumping over by one. So delta y times d over L, and notice how the m's are going to cancel. if I do equation 2 minus equation 1. So another formula that you can use in the small angle approximation is the distance from one bright spot to the next. Now, and this is the easiest thing to measure, right? If you looked at the demo, what you can do is you just pull up a ruler next to the bright spots, and this is the thing that you would measure. Really, you would measure like 10 of them and divide by 10 to accurately get the distance from one to the next, because maybe it's just a couple of millimeters. It's hard to measure. But you can measure that accurately. And this gives you a way of measuring, say, the wavelength of the light, or the slit separation. Right? So this is actually a tool to help you measure small distances. And when we talk about single slit diffraction, this is a neat tool to measure small things. So something I'll talk about in a later video is you can measure the width of your hair by just shining a laser light on it and then looking at the diffraction pattern and seeing how far apart the interference maxima or minima are. We'll talk about that in a later video. Okay, so let's address this problem. What happens to delta y1 if we replace the red laser with a green one? So we're going to decrease lambda. Okay, so we're going to address the original problem here. So original problem. What happens if we replace lambda with a new one? So we can do delta y1 old over delta y1 new. Or why don't we do new over old rather than old over new? Is equal to, so notice how in this formula right here, notice how we're not changing capital L, we're not changing the slit separation D, we're just changing the wavelength of light. We're changing the laser. So we're changing the color of the laser, so we're changing the wavelength of light. And they're directly proportional. So delta y1 is proportional to lambda. So this is going to be the new lambda over the old lambda. So in other words, delta y1, the new distance between bright spots, is going to be the old distance between bright spots times this factor of, so the new wavelength, I think it was green light of 530. So it's 530 and 650. So we have 530 nanometers, and we have 650 nanometers. And I don't even have to write the nanometers because those units are immediately going to cancel each other out. So it looks like delta y will decrease, and we know exactly by what factor it'll decrease. So delta y decreases. In other words, those bright spots are getting closer together. Okay, so in the demo, you also, they tell you, there's a part of it where there's, they shine light, 3 different colors of light on the same slits, the same slit distance, and you can see the difference in distances for the different colors. And you'll see that like green light will be close, that will have fringes that are closer together, right? Fringes that are closer together than red ones. And blue would be even closer. Yeah. Okay, the last thing is the intensity of light. So in a lot of one reason that this topic tends to be confusing is that books will do a lot of things with the same diagram. So right here, what I was doing before was I was drawing the bright fringes as, like I put a bright spot, bright spot, bright spot. So other books won't do that, and they'll be more quantitative right away. So right now, by the way, I'm turning the tablet 90 degrees. And what I'm doing now is, so along this center line, so now I'm going to make a plot. So something versus something. And what I'm going to plot is intensity of light. So wherever I see a bright spot, that's where it's maximal intensity. And that dark spot is where it's 0 intensity. So actually, there's a quantitative relationship for exactly where you are on the screen and the intensity of the light. And so this could be y or angle theta. So I guess your book writes this in terms of y. Yeah, I'll do that too. I'll just put I versus y. But you can also do I versus theta. Remember, we're just labeling points on the screen. We could do that with either a y or a theta. So this diagram is kind of weird, right? It's a physical picture. Like what I drew in black is the two slits on the left and then the screen on the right. And then all of a sudden we just turned it into a mathematical like function, right? Intensity. So this thing right here is intensity as a function of position on the screen. So your book shows, I guess it's just referencing chapter 17 where they go into more mathematical detail. But the intensity goes like a cosine squared. So the intensity is proportional to, so it's going to be some amplitude, which I'll hold off for just a second. It's cosine squared of, I'm going to write it, the easiest way for me to remember this is it depends on the path length difference. And anytime the path length difference is an integer multiple of lambda, or sorry, the phase difference, anytime the phase difference is 360, or sorry, 2 pi, then we should get a maximum right there. So let me write, so the phase difference over 2. So I just want you to look at this and convince yourself that this is actually okay. So if the phase difference, so if that delta phi, if that's 0, then we get maximal intensity. Cosine squared is 1. If delta phi is 2 pi, plus or minus 2 pi, which is the bright spots that are closest to the m equals 0 bright spot, m equals plus or minus 1. So if delta phi is plus or minus 2 pi, we get cosine squared of pi plus or minus pi, which is also 1. So this is exactly the relationship. So given that we know it's a cosine squared, it's going to relate to phase difference like that. So I'll just put I max right here for now. And then what your book does is just rewrite. So remember, we can always rewrite phase difference in terms of path length difference. We talked about that in the chapter 17 video. And then the path length difference, we had a formula for that in this video. So your book does those 2 steps and it writes this this piece inside the cosine squared in terms of y. You get pi times d over lambda L. So as some practice, you might want to make sure that you can reproduce that step. So pi times d over lambda L y. And it looks like, notice how they use the small angle approximation to rewrite y over L for theta, or for sine theta. Now, a quick comment. So they're assuming that so the average intensity that goes in here is I1 for each of these. And if that's the case, then this maximum intensity is not 2I1 but 4I1. And the reason for that is when you average over position, some of the time it's 0, some of the times it's more than 2I1. And that's where this 4I1 comes from. So notice how if you take the average over all positions for this side of the equation, the average of a cosine squared is 1/2. So if you average over the whole screen, you get 2I1. So this is just the statement that energy is conserved. So the amount of light the amount of energy that's entering here plus the amount of energy that's entering here eventually winds up on the screen. So if the intensities of each of these is I1 and I1, this needs to be 4I1 in order for energy to be conserved. Oops, I forgot the square right there. Okay, so this is intensity as a function of phase difference, but you can easily write that in terms of y also, which we just did above. Okay, yeah, definitely check out the Khan Academy for a slightly different way of approaching this, but I think that one's pretty good too. Oh, by the way, it's cosine squared, but it actually drops off a little bit, and this is the effect of the slits having a finite width. So we're going to talk about that when we talk about diffraction in sections 4 and 5.